Okay, Martin, we should get going. It's 5 after.
Okay. You can see my screen, right?
Yes.
Okay, great. So I have two models that I have prepared. So it's the super resolution. It's from this one, super resolution model, and then the transformer, or self-attention. It's also here somewhere. Self-attention. Okay.
Yeah, it's I think way up.
Okay. Yeah.
Before even the ordering. But yeah.
Yep. Right. Pixel CN. This is the one, I think, or this one. Yeah, those two. Anyway, it's here somewhere. And then, yeah, those are the two ones I prepared. There's much more models, but I think we can just get through these two. Okay, so the idea of super resolution here is that so you can give a lower low resolution image, and then we'll ask the network to recreate the higher resolution one. It's a little bit weird here because the input is actually a grayscale image, and then the output is actually a black and white image. So it looks weird this way because our MNIST image is binary here, the one we're using. But when we rescale it, it turns it into float, and then it becomes a float image. So here's the code for it. So they don't give us the training code, so I had to kind of add some code. So hopefully they're correct on what I added. But the basic idea is same as before with pixel CNN, but we had that one thing, the conditional size. We have an extra this conditional size. So if it's equal to 3, it means that we're getting a subsample image. Then it creates a network. So the point of this is to take the low resolution sample and upscale it to the regular size. And as we'll see, the reason for this is that this function is called here. So the first thing that happens if we are sending the conditional is that the conditional is converted into a bigger image. And if we go through here, yeah, and then as we can see, it goes into MassCon 2Ds. It's passed over here. And what we do here with the conditional is it's this condition here. Sorry, it's yeah. So kind of so here the conditional is again there's another convolution here, and it creates an image of the right size and adds it to the output image that pixel CNN would usually have. Right, so that's all that's happening. So I can show it into the debugger. I think that maybe that would be more interesting. This is kind of slow running. I think it's because I had to do a lot of typecasting. It floats and UINs. I couldn't figure out how to make it work. without typecasting all over the place. So that's probably making it super slow. But so here we have X, which is our input data. So I can, yep. I've already done this. So this is the actual data that we're getting. You know, this is just one of the images. You can see it's an 8, or if we want to look at another one, I think. Oh, oh, sorry, probably should be the first one. Yeah, it has 120. So these are the images, right? So, and then if we look at the conditional, it's a subsampled one that it's a low resolution version of the number, and this is just using the oh, sorry. This is just using the interpolate. So when we do the training, we have to take the image, get the low resolution version of it, and get conditional, which just interpolates it to 1/4 of the size, and then we pass it to the loss function when it calculates the loss function. The loss function calls the forward and all that. So as we can see, it goes from NL. I think instead of loss, or they change the name to NL in this package, and it calls it here the forward. Okay. So when it calls here, then it will go to the masscom 2D, and so if we look here, yeah, I do have it bookmarked, so I can just jump over there, and it will take our conditional. So the one that we passed with the subsampled resampled image. Here it's in tensor, so you can't really see the shape. But what it does is it goes through the conditional operation and then resizes it. As we can see, conditional opt-out is 128 by 64 by 28 by 28, and then output out is the same size. So it's just everything is added together. And I can show the conn.op. Oops, that's not the right one. Yeah, and since we just started training, it really doesn't know. It just creates a grayscale image, and it's like, oh, this is what it should be. And this is the first round, so it doesn't look like much. But so what happens is the one that's created from the conditional operation, and then the one created by the pixel CNN, the regular pixel CNN, they're added together. And so in the loss function, if they don't match up, because we just have cross entropy with the self and the condition, and then the actual image. So if the added image generated by the conditional doesn't match up, then there's more error. So it will minimize the original image as well as resampling the conditional image, so that they both produce the same result, right? So does that make sense? How they're doing super resolution? Is there anything that?
Yep. So they mix in the condition with the original image, then compare it to the original image and reduce the loss.
Yep. And so, yeah, it's pretty straightforward like that. You just, you have a separate sort of a branch here. I can Yeah, the
Yeah, in
conditional
fact, if you right, yeah, that sequential. In fact, right there, the code is how it gets it from 7 by 7 to 14 by 14 and then 28 by 28, right?
Yep. Yep.
Because each of them, when you do the scaling by a factor of 2, you go from 7 by 7 to 14 by 14 and then 14 by 14 to 28 by 28.
Yep. And the network where we can see the output sizes doesn't work because there's a conditional, and so that library doesn't allow, didn't think of passing a conditional, so we only get the shape of it. So it doesn't, we don't, without going through the forward, we can't tell the size, right? So it just we can only show this, but this is the conditional operation, and then each Con2D also has their own little conditional operation. So there's 2 different networks that is upsampling, and then the usual Con2D is also going on. I'm sorry, the usual pixel CNN is also going on. So that there's the mask and all of that. Otherwise, if you can see ahead, and then it will just predict everything. It will just use that original image to create the distribution. Yeah, okay, we're here, and okay, yeah. So this is the output from the conditional, and then we just go back to okay, yeah. Yeah, we're just here, and then we return out. I can just see. Oops. Okay, it went there again. Okay, and then the output is 128 by 1 by 28 by 28. So it has a probability of each value. Okay, and so let me run this one time through. It does take a while. Oh yeah, let me. So I added this callback so that after each epoch, it can after each epoch we can just visualize it like in the collab notebooks. And the basic idea is, how do we sample it? We just say this is the size and here's the conditional, and the conditional is just the test data that's been resampled, right? So get conditional resamples it, and we just take the first 32 values and then we resample it, and then all of these 32 should be reconstructed. If we look here, it's the same one as before. Only thing is that the condition is passed on to the network, and then the samples are generated with the conditional, one pixel at a time. And something should show up soon. It does take a long time. I was having a lot of trouble with this. So I didn't realize that this one, when we interpolate it, we start getting a float tensor. So before it is always a byte with 0 or 1, and then becomes a float tensor. Okay, I think it should be breaking soon. Okay, so I'd like to check. I was just going to check that this produced it. So so this is the output from the first epoch. The error is already pretty low, 0.0719. And from what I've done, it doesn't improve all that much. I think I have it somewhere here. Oh, it's already cleared out. It doesn't improve dramatically. But as you can see, we have this grayscale low resolution one, and then it improves it drastically. And this one, I don't know what it was, but it couldn't improve it. But as you can see, this is the grayscale, and this is a binary image. So it would probably be more interesting if this was also a grayscale image, or maybe it would have better results probably. But yeah, I was gonna see just visualize the conditional. So conditional NP. Oh. Okay, it's all zeros here. So okay. Don't know where it's coming from. I think it's just starting with a new one. Yeah, I was hoping we could show the resolution working. But oh, I think we have to go back one step. Anyway, that's the basic idea. So this should be the array from, this is probably a 0 or something like that. And then if we look at the, if we take one extra step, and then we look at conditional again. Didn't show it. It's all zeros here. So, some numbers here. I don't know what's going on. Okay. Yeah. But that's just the general idea, I guess. Yeah, it's not quite working. Something's could see the output of it. But that's not happening for some reason. Oh, it's 64 by 28 by 20. And then about maybe this one can be something visible. And so this is the super sampled image. And this is probably, this is grayscale. Oh, where's the, so there's the kind of the 0 that's there. Right, so that's what I was trying to show. So it took a while, but I think the one before on this case has a different size, so it's not a 2-dimensional. So that's why it was not showing. But yeah, that's the general idea. So you have you have the subsampled image, and then you superimpose it over the original image, and then take the loss. And so if the super sampled image is bad, then the loss becomes higher. So as long, and it will incentivize it to become as close to the original as possible. Right. So
the idea basically is conditioning on the smaller images, but to get images beyond the original image size, right? Because actually in this case, no, they just blow it up. But getting back, it just gets back to the 28 by 28. It doesn't go beyond that, correct?
Yep, it's just 28 by 28.
Beyond, I mean, it's not any bigger. It's just conditioning on a smaller image in order to get better resolution at 28 by 28.
Yep.
Okay.
I don't know how it would work to do to do that you can train on a lower resolution and make it output a resolution higher. I think it's possible, but it will probably be confused because all the dimensions are hardwired everywhere, right? So it will learn the loss function from a certain hardwired size. So, but yeah. Yeah. Okay. So that's a sort of like a simplistic. It's a super sampling, just based on the image.
But it's basically an extension of the conditioning, right? You can condition on color, you can condition on the class, or you can condition on the size of the image, thereby having super resolution by the time you get to the original size.
Yeah, it's the color is not really conditioned. I think that when they say conditioning, it means that they're going to add something on. So with class conditioning, what they did was just basically take the class and broadcast it all over the image. Just add that class onto the image, right? And so I think that it's the same idea that you're taking the image and putting on top of it, and then minimizing that loss. But yeah, in that case, but color conditioning is you're not adding two images on top of each other. It is like a conditional, probably like a conditional versus a conditioning, or maybe.
Yeah. In the color case, it's more that within the mass, you condition the green to only get from the red, and then the blue to only get from or to get from both R and G, and R doesn't, it's kind of independent, right?
Yep.
We saw that earlier, yeah.
Yep, and at each iteration, it produces all three RGB values. So
right. In fact, the other thing is the grayscale example in the Colab notebook where they show hierarchy, or it's under the hierarchy term. That one also seems to be an example of conditioning, that it's just basically the grayscale is 2 bits, and then it's actually in the that one, but also in the Colab notebook. So
okay, yeah.
Right. So you first condition on the 2 bits, and then you condition, and then you use the color. So if you see, much like when you do the conditioning on the size, you combine the two, right? If you're saying that you combine the regular pixel CNN and the or the regular size and the lower size blown up, and you combine them, and then you take the loss. So similarly, in this case, you see the when you look at the loss, they do the combination of the losses. In fact, it's clearer in the Colab notebook code. If you see, they just combine the NLL of the gray and the if you go down, yeah, that one. And if you look at the negative law likelihood, it's the combination of color and gray. So, and the gray scale is just the pixel CNN of the grayscale with 2 color bits, and then the color aspect, and then you just combine the two. So it seems like that. I don't know why it's called hierarchy, other than maybe it's 2 levels of conditioning, meaning first you do the grayscale, then you condition the color on the grayscale. But that's essentially just seems to be a variation on the conditioning, right? At least that's the way I understood it by going through just looking at the code and running it, right? Because it seems very similar to what you just explained with respect to the size. In this case, there is no difference in the size of the 2 images. It's just that one is quantized to 2 bits and the other is quantized, I think, to 4-bit color. So you first do the 2 bits and then you condition the 4 bits on the 2 bits and then combine the loss.
So does it result like in better shapes of the outputs? So what is the motivation? I'm sorry, I kind of haven't gone through it in the details. So
yeah, I think in this case, Arto, my understanding, and I'm willing to be corrected because I didn't spend tremendous amount of time, but I thought in this case it's just the fact that they were doing it on the color MNIST database, which does have color, but 4-bit color added to the underlying or the MNIST data. And I think it's, to my understanding, they were just trying to illustrate yet another variation on conditioning. So you can condition on, the size, as Mohandas showed us, and you can condition on the class. And then this
okay,
is like,
just judging from the samples, it looks like they want to preserve the image perfectly, right? But add the colors. So that's right. Okay, then.
Yeah. So that's what this shows, that you can, if color is added to an image, meaning in colored MNIST, as apparently it's called, and it's 4-bit color, not like, the full RGB color. It's just 4-bit color. So you do the 2 bits grayscale, and then on top of it, you condition the color on the underlying grayscale image. And that gives, I guess, a good representation of both the figure and the color, which is the colored MNIST.
Yeah, so this approach can kind of be applied to other coloring setting, right? Like this, coloring the old photographs, right? So
Oh, yeah.
Fit in the old
thing
photograph.
Right. But the thing I don't quite know is, they show it for a 4-bit color case. What I don't know is, when you do it for like 16, 64-bit colors and stuff, how much the output scales well. I can't think of a reason why it shouldn't, but I'm just saying, don't know.
Yeah, but it looks to me like this UNet architectures are usually applied for that kind of problem, right? But
yes.
that's kind of alternative approach. I have no idea if the pixel CNN is used like in some kind of like practical setting for this kind of problems, but it's kind of interesting demonstration how you can mix the information, right?
Yep, that's what I took away, that here is another dimension along which you can condition. Class, then size of image, and then also color, which would be more along the quantizing and the channels. Okay, Mochen.
Okay. Yeah. Yeah. From what I've the Wavenet is used heavily in speech generation. I think it's the state of the art in speech generation. But I think for images, I don't know if the masking techniques that we've used is used heavily for image or not. I'm not sure. So, but the speech generation part where you can the class condition, the voice, like I want this person kind of voice to come out, or accents, things like that. I think that they've got it all in there also. From
Yeah, that's a good example of, excellent example of the conditional thing. You could have a male or a female voice, or you could have the accent, and those are all you can condition the audio on that. Yeah.
And
very good example.
Yeah, and I believe the state of the art, the generators, still use Wavenet, but not for images. I think the GAN styles are, or I don't know much about GAN, so I still don't know much about. But anyway, but I think all of these techniques have the same idea that there's masking, right? The previous pixel, there's a distribution of a pixel given all the pixels that came before it, right? All have the same basic idea in MADE and pixel CNN. Okay, so I'll move on to the next one, the transformer one. So okay, I think we might have to go a little bit into the model. This is just called the transformer model, and we're using the same data. So these I copy pasted these, so we don't need the labels, but it's a transformer model. And if we look at it here, it's kind of convoluted here, but okay, so from what I know, the basic theory is, let me find the transformer picture. So if it's kind of boring, but let me, people can correct me if I'm wrong. So whatever picture you have to first turn it into an embedding. So in the NLP, they have they turn the word or part of the word into a word to vec or something like that, right? And then you add the positional encoding, and then you can have these stacks of encoders and decoders. So this is where the masking goes on. So that's where we're going to be interested in. So in this one, we have to figure out what does this mean? What does the embedding mean? How do we do the positional one? How do we do the masking? In the current architecture, they leave out the left-hand side encoder part, and then they leave out the this multi-head attention one. So it's just masked, and then it goes directly to feed forward. And there's two of them, two layers. So I can show you the architecture here. So if we go here, everything is hard-coded here. So there's the linear, but we we have to make sure that we send in the data. And this is a positional encoding. So we don't use this one, or mode is pixel location. So we're not using this one. So we have a linear layer, and then we have, this is number of layers is 2 here, because it's hard coded right here. You can change it, I guess, but and so we have 2 decoder layers. So as we said, this is the picture. This is called the encoder, and this is called the decoder. So it only has 2 decoder, but it's their own decoder with only the mask multi-head attention and then the feed forward. And then the output is just a linear.
Yeah, what I thought was interesting was that unlike in the case of the NLP situation, here they explicitly say in the Colab notebook that positional encoding doesn't work, and you have to actually give it a position, and that's why they don't use that option, which I thought was interesting, because in the traditional or conventional NLP-oriented transformer, it's given this sinusoidal positional encoding thing, but that doesn't work here. Apparently, the thing that works is this pixel location.
If you remember that notebook I shared after the lecture, I guess.
Yes.
Sometime.
Yeah.
So I've just fed in the
somewhere here
pictures as is, and I've used I don't remember what kind of positional encoding, probably just as this like sinusoidal or just learned positional embeddings, but I've used just regular stuff which is used in NLP, and worked fine, especially with
cool.
class conditioning. And I haven't really spent much time on training it, but yeah, I've used a deeper model as I used 2 layers, and I had I don't remember, but probably 6 to 8 layers. And yeah, so it's very simplified kind of problem setting, because I only have 2 binary values for the pixels. It's either 1 or 0, and I can scroll down to the results. Probably I just broke the training in between because it was taking a lot of time.
Okay.
And here you can see that with class conditioning, the results are quite good just after some not very long time training.
Yeah, how many epochs did you train for?
You can scroll up and see just a bit. Yeah, so here you see that there is 3 epochs, and it is kind of, I terminated it halfway through the next epoch. And yeah, so here the problem was the generation was really slow, but you can speed it up by really significantly by caching the keys and values. Yeah, I think yeah, we can go through the collab by their course authors, and maybe if we will have time, we can come back to that, or I can share some links that might be found useful if you are interested in applying transformers to this problem.
Okay, yeah, that sounds great. Yeah, I can quickly go over the approach given by the authors, and then maybe you can say more about the approach. But okay, let me go through it a little bit quickly. Okay, so so is that okay? Does it sound good?
Yeah, sure, be fine. Go ahead. Yeah.
Okay. So let me just see what the decoder layer has. and we can just, so as we said, it just has the multi-head attention and then the positional feed forward. As we said, just from the picture, these two things, the multi-head attention is it's a masked version of it, and then the feed forward one. And then if we look at the multi-head, and I think there's another picture that we need to find for this. Yeah, this one. So this is the trident. So the input becomes 3 different inputs, and then it's a linear, and then there's a attention matrix and all of that. So it's all here. They make it sound like you have to send 3, but if you look at the decoder layer, it's just sending the same output 3 times. So I don't think they ever are different. So that's a strange way of doing it. But anyway, they could have just done it here. Yeah, and so yeah, you can see you just multiply these 3 linear layers, and then there's the attention, and then scale dot product, and this is just here it is. It's the Q, which is this value divided by the temperature times K transpose. I think all of these are in the paper. Which operation? It's somewhere here. You've probably seen all of these if you've gone through transformers. It's just the basics of how transformers work. There's just a sequence of pre-specified way of doing things. So you have the you multiply it, you divide it by the query size, you take the softmax, and then you multiply it by the fourth one, and that's all. All of it is just follows the exact same thing. Take Q, take the temp, divide by the temperature. There's a transpose. Okay, so the only thing is the mask, and and as we can expect here, the only place that mask is applied is in this attention part. So when they calculate this, do this, and then it produces an attention vector. Yeah, maybe this is the picture, or this is the attention score right here. Then they apply the mask to this. And the attention is supposed to be like how much does first pixel pay attention to the second pixel? I mean, and if I run this here, see if I can run this. Okay, so that's also location we got to talk about. I forgot to do the so also needed to talk about the mask, which was somewhere here. What the heck? It's being sent here. Somewhere the mask is being created. I forgot where it is. In one of the inits. Forward mask, forward scale. Okay. Okay, self.attention, and it should be here. Mask equals mask, and this is the masks that is being was created. So I just wanted to see. No, this is also being passed. Okay, sorry, I want more level up. Multi-head attention. Transformer has the mask in it. Oh, here it is. Okay. So if we can get here, we can show the mask that they're doing, and it's exactly as we expect. Self.mask. This is a tensor. Okay, let me quickly do this. And so if we look at the mask, it's just a lower triangular or upper triangular, I guess. So 0, 0 cannot see itself, and so 0 cannot see anything before, and 1 can only see. So they create the attention vector, attention matrix, which says which pixels should pay attention to what, and then they zero out everything that's below the diagonal. So a newer pixel cannot pay attention to an older pixel cannot pay attention to a newer one, but a newer one can look at all the older ones. So that's where the masking happens, and it's just another way that they created here, and then they pass it 2 levels down, but it is being applied way down here. Oops, sorry, overshot. Yeah, in positional encoding, yep, this one. So if the mask is 0, then the attention gets huge negative number, which probably means don't pay attention at all, right? So if
I was going to say, in this case, it seems like, I mean, our understanding thus far is flipped, right? Meaning if it's 1, then if it's 0, then it means that it's allowed, but if it's 1, then it's masked. Is that right?
No, if it's 0 means you're not allowed, I think. So for 0, all of these are 0. So if the mask is 0, then you're not allowed to pay attention to it. So the first pixel is not allowed to pay attention to any of the other pixels. So this masked fill is like the saying if this is true, then set this value. I think this is a built-in function in tensors.
So mask, if mask is 0, you set it to 1e minus.
Yep. To a big negative number.
Sorry. Right. Which would then, in the equation, because it's exponentiated, wouldn't that basically result in it being zeroed out? That is, the mask.
Oh, with the softmax, you mean?
Yeah. Because the thing, if you just look at what you have, and I may be wrong, but if we just look at the stuff you have, traditionally what we want to allow is things above and to the left, correct? Of an 2x2 image. Or in this case, maybe we just look at it row by row, then it would be everything to the left. Then it's probably a 1 means allow, but a 0 means mask.
I think in this case, we have like sequential representation of an image. So we are like unrolling it in some order, row by row, maybe. So, the masking is just causal masking. It's very similar to that applied in NLP, but usually it's implemented in a way that self-attention is allowed, but you shift the target with respect to the input. And here they just disallow self-attention, right? But it's essentially it's kind of have the same result.
But it's row by row.
Yeah, it's row by row. So in this case, you can see that basically the pixel number 1 is conditioned only on pixel 0. And then pixel 2 is conditioned on pixel 0 and pixel 1. So that's this triangular mask. It kind of disallows attention to everything that comes after a certain pixel. And in this particular case, it also disallows self-attention. Like by self-attention, I mean attending to itself, not the.
Yeah.
Okay.
Yeah, that's kind of like the A version of the mask, right? Meaning in our traditional thing, it's mask A versus mask B. So mask A is also not allowed for any pixel. Mask B is kind of like only pixels before it. And maybe, as you said, because it's flattened, there's only the before concept. So it's only the second pixel would only allow the first, again, if we are 0 based, then the first just allows 0, the second just allows 0 and 1, the third just allows 0, 1, 2, and on and on.
Yeah. And as it was mentioned in one of the recent PyTorch deep learning sessions, that basically transformers operate on sets, which in other words, the transformer architecture itself has no encoded
orientation or
order, right?
Yeah.
And this order information is only obtained from the positional encodings. So basically, I guess if we shuffle the pixels, it would be closer to like this fully connected networks based stuff. If we shuffle the positional encodings accordingly as well, So if we shuffle both pixels and but still have proper positional encodings for each pixel, it wouldn't matter that much.
That's like changing the order.
Yeah. So it would be the same as we discussed for the MAID. That obviously some ordering work better than others, but that's not because of architecture. That's because of the data.
Right. Yeah.
And convolutional networks basically rely on this, local patterns, and if you would shuffle the pixels in an image, and then you cannot effectively or efficiently apply CNN-based architectures, right?
Yeah, because you lose the locality and the hierarchy and all that.
Yeah, and
insightful. Thanks.
Yeah, well, what I wanted to show was the attention matrix. I mean, it's exactly as we expect, but just all of these top parts are set to 0, or I'm sorry, set to this large negative number.
Large negative.
Yeah, and I think if we go one more step and look at the softmax, I think they all become 0. Let's see, one more step, and then I have to redo that step again. Okay. Yep, they're all zeroed out except this guy, the first one.
The first one is not zeroed out because every value is the same. So after softmax, it remains the same as well. Should remain the same as well. But it's actually it's not. I see some zeros there. So
Yeah, I don't know.
So those probably some numerical stuff, or I don't know.
Yeah, but I think after softmax and all of that, then it becomes 0. Yeah, and then okay, so that's the masking part. The other other part is the positional encodings. So I think it's a little bit strange the way they did this. So we have our X, which is the image, and it's of size 128 by 28. So, you know, if we just look at X, let's just look at one sample of X. It's kind of painful having to do this every time, but hopefully next version they can just be able to see tensors. But this is our 7, right? And so, and to create the location, they have this locks array. And I think it's just better to look at the visualization of it. And it basically goes from 0 to 1, and it's repeated the same way. So here, this is, so you can think of these at the X values, and if we look at the Y values, 128. Oh. And this is the Y dimension. So
yeah,
here,
actually, I spent just if I finish up, and then I spent some time trying to understand how they generated it. It's kind of quite useful code in the future too, if you want to generate like the coordinates of 28 by 28 array and how they did it with a few lines of code. So I can get into it after you and Nat were done, if anybody's interested. But yeah, I was curious how they did it, and they've done it, at least to me, a fairly clever way. So just 3-4 lines of code.
Yeah, and so the way it occurs is that when we get and then they permute it, and torch cat. I'm not sure what this line does, but let's look at X again. So this has, so the first column is the actual data, second is the X coordinate, and then the third one is the Y coordinate, or Y and X. But so that's kind of how they represent the data here.
Yeah, they concatenate the X and Y coordinate, and they do it by mapping the 28 by 28 onto a 0 by 1 axis, and then generating the X and Y coordinates for such a thing, and then sticking that X and Y after every pixels. So that, but just how they generate the X and Y for a 28 by 28 array, I wanted to understand, and so I kind of took that code and stepped through it, each step, and I can share what they do to get to the result in like 3-4 lines.
Okay, yeah, and so this is the first ReLU here. I should look at this here. This, I made the output of the model. So this is the model, if you can have it run through all the forwards. So the first thing is the linear model. And so they turned this this shape into a 784 by 64. So I think it's basically acting as it's basically acting as this part, the embedding. So we have the pixels, we have the positional encoding, and there's a linear that happens before it goes into this decoder structure. So I think my question was like, this one doesn't have masks, so I don't know how they're making sure. I don't know if just masking the attention is enough, because here the neural network, I'm sorry, the fully connected network is going to mix everything together. So I thought that was here, right here. Sorry, this one. I don't know if this is a problem.
No problems there, because this fully connected network operates element-wise. So it treats every vector like this embedding. If you think about it, we have the input in a shape, like if you can like check the input shape, it would be batch size, then sequence length, and then, okay, for
input size X, okay. Yeah, 128.
Yeah, so here you can see that it is batch size, sequence length, and the embedding size. So yeah, I think its input has 3 like values, but inside the model it should be something bigger, yeah. Right?
So the 3 is the value of the pixel, the X, and the Y coordinate.
All right, but in the model, it would have some d-model dimension.
Yeah, and it gets the linear one, turns it into 784 by 64.
So so the fully connected operation is done only on this last dimension. So every of these 784 values are treated independently.
Okay.
So no, there is no kind of information flow between those, and that's why, you know, often this kind of operation, it's not exactly like dense subnetwork, but might be considered as convolutional subnetwork.
Okay. Okay.
So it's kind of equivalent to one by one convolutions, you know. Okay. So we just deal with this last dimension. Okay.
Yep, just we're squishing the last one, the X, Y, and the pixel value together, but not mixing any of them, right?
Yeah, but by the moment we apply this this network, we will not have like pixel value X and Y, but we will have like this 64-dimensional embedding of this information.
Okay. Okay, that makes
the
it.
Goal in this case, then what you're saying that the goal is just convert the dimension 3 to a dimension 60 for each input, but each input is done independently, and that's what kind of equals one-by-one convolution.
Yeah, yeah.
Yep. Okay, so that's so that is the I guess the embedding part, that we can get the positional encoding. It's 2 columns, and this is the actual image, and we just straighten it out, and then we have and we have one-by-one convolution that goes through and produces the input for this, and we have 2 stacks of these. Yeah, and this is forward force transformer. Okay, and then at the end of it all, yep, and when you return back, X is 128 by 1 by 28 by 28. So that gives us the probability of 0 or 1. Okay, and so besides that, I think this is so besides that, the standard transformer, and I didn't go through this one. This is also a pretty standard to do a linear normalization, ReLUs, a linear one, linear, dropout. And this is the skip connection where we add the actual residual to it. So just like the picture, nothing complicated, right? So anything that can also be added here. But I think the order is slightly different. So they added after all of it, not before it, but because this is added at the end.
Majan, sorry to interrupt. There is a
Sure,
question
go ahead.
in the chat
Oh,
about how to visualize matrices in PyCharm.
oh, no, you don't need anything. I think it's just if it's NumPy, it will show up. Yeah, just any NumPy. It won't do it for tensors, unfortunately, if you convert them to NumPy, but it's built in. But it would be good if there was extension that you could use to also do it for tensors. And also have a 3D. Sure. Go ahead.
On that subject, one of the things I had not yet, just code a PyCharm to code, and I was curious. Somebody knew within Jupyter Notebook itself, what's the best kind of find out some of the code modules. I was having time locate, for example, the decoder. Is it with transformer, or is it, even it's within specific modules, need to figure out it. Tips on how best to do that. I mean, obviously, we have VS Code, then it makes tremendous helpful, but I was just wondering if anybody had any way to figure out where modules are buried, how best to access it.
I think you're cutting out a little bit, but yeah. But from what I know, it's very hard. That's why I use PyCharm, because maybe Jupyter has become better, but in this one, it's the actual thing is here, and I commented those out, but like they get the so they download some package and install it in the Jupyter Notebook. So it's inside the VM or something like that, with whatever the Jupyter Notebook runs on. And I think you can go into it. You can like do SSH into it or something like that. I'm not sure, but then yeah, it's hard to do. In PyCharm, all the stuff is in the virtual environment, which is in the same. You can choose where you want, so all your packages get lib site packages are here. So your what is it called? Homeworks, help, DPUL. So all of the stuff is here. So these are the two packages that we use. So it's all here, and you can just go in and you can even edit it, and then it will run it. But I feel like the Jupyter Notebook, while it's running in HTML5, is a little bit harder to do.
Quite hard. Some of them I couldn't even find the code easily. For example, code a layer or a couple of others. Obviously, if it's a more thin or it was easy, but otherwise, the approach, you need a VS Code or something like that, really getting details. So that's why I asked the question, if anybody had any tips but I've really hard and had so I need to in VS.
Yep. Also,
Okay.
my PyCharm is actually the professional version. I think they have extra support for the Jupyter notebooks than the community edition. I think that when the community edition is, but maybe they fixed it. So I've had this for a while, so I have the subscription. Yep,
Good to know. Thanks.
Okay.
Yeah, I think there is a visual debugger extension for Jupyter Lab,
Okay.
but I haven't used it much. And yeah, VS Code is with native support for Jupyter notebooks. It just, I think it's just more convenient now.
Yeah. Without it, I found it. I could locate modules, and it's what I found hard going. Just have to do it. Code, I guess.
Yeah, but
Thanks.
if we talk
Let's keep
about
going.
browsing source code from Jupyter, it's really easy by just, you type in the name of your function or module and double question mark, and then the source code is printed in your output. So
Yes,
browsing source code is really.
Yeah, that trick is a lot, but in some cases, for example, I was able to get the code easily. But for example, in this thing, I was trying to, Mochen is sharing some, right? Like I was trying to the decoder layer, and I had a hard time figuring out where in the hierarchy or something layer was. That made it really, as he can, with PyCharm, you can go on the thing that you just did and click and it shows up, but it's not in Jupyter. Because if you do decoder, it just said not found. And then, searching for exactly it's buried. And finally, like deep UL has it's there on, but if you go the deep UL helper utility some of the functions actually uses are there in the GitHub. So it's something that downloading of the library from, which is not what is GitHub code. So I was lost.
Yeah, there is also an extension for browsing code from GitHub, but I also couldn't make it work nicely, so I just dropped it, because now you can browse code from GitHub itself quite conveniently, I guess.
Thanks.
Okay. Yeah, and so going back to the transformers, I think that's all it is. And yeah, it's the same sampling technique as before. You just take the take the value and then keep asking for it and do a Bernoulli. And I can just run right. Oh, if I get rid of all the so for after each epoch, it shows me the picture. So just like the notebooks, I added that so it does a callback. Does a callback, and it just does some samples. I don't know if this causes the training to be disrupted, but yeah, it does take a little bit of time to get through one. Oh, here we go. That's one of them. It should produce the image soon. Oh. Yep. So this is the results from the first iteration, and so this is just generating without any conditional is just generating, randomly, just like with pixel CNN. Right? This is the first epoch, and I think we can just do epoch 1 and then actually have it here. So you can actually look at it. This was epoch 0, epoch 1, epoch 2, epoch 3, 4. I probably should have mentioned the epoch, and then sort of it was getting a little bit better. So this is the new one that came from epoch 1. So this is kind of the output it has, but yeah, it is it is doing the training right now. Okay. Oh, there's something in the chat. Yeah. Okay. It's in the professional version. Yeah, I've had professional version for a while, so because I do use it for work, and I have the full package with all of their tools. So yeah, I use it all every day, all day. So it's worth the investment for me. And yeah. Okay, yeah, that's all I have for the for my presentation. I'll stop.
Then Arto, you want to share your stuff? That'd be great.
All right, yeah, I can quickly share just to let me. All right. Yeah, here I can show you this demo notebook from this like project, and there is a paper which basically is about like linear attention. That's one of the attempts to like linearize this attention operation, and they use like image MNIST images generation as a demo. And here, so what I wanted to like share. Okay, so here the first thing here, they also use just regular positional encoding. So you can see here this is kind of like static positional encodings, sinusoidal and cosine embeddings, and that is used for this model. And yeah, so and the problem with transformers is that when you generate next pixel, it is conditioned on all the previous pixels. But you can speed up this process by caching the keys and values, right? So you're trying to generate value, say for this pixel, and like if you do it naively, you get to compute all the keys and values for this for all previous for sequence of previous pixels. And as you go like down the image, the sequence becomes longer, and with softmax, like standard dot product softmax attention, you have a quadratic time complexity with respect to sequence length, so that makes it even slower. And so that's why the naive sampling from this transformer would be very slow. But you can do this trick with caching the values. And here the authors have bunch of experiments showing their like timings, and here you can see that on CPU it takes to like they generate 100 images, and it on CPU it takes 30 seconds with the linear attention module, and like about 200 seconds with regular softmax attention, and that's with this caching. Okay, but it's on collab CPU, it's quite slow itself. And with GPU, the speed up is quite significant. You can see that you can generate the images in 5 seconds if you are using this linearized attention. And yeah, so softmax attention is still quite slow. And yeah, here they have like this plot showing how the time taken to generate the attention scales with sequence lengths, and you can see that it's quite bad for softmax attention. So that's why it's kind of hard to generate images with regular transformers. Okay, but if you use there are a lot of this kind of linearization of attention, and yeah, you can see that it's much better if you use it. Okay, and I can show you how they do this caching in the code, and yeah, well, you can, like, for example, in if you use Hugging Face transformers, it's also implemented there. So if you are using Hugging Face transformers for some kind of generation, you probably use this caching of intermediate values as well. So basically, you can see that here this forward function takes in like query, key, and value, and also a state. And a state contains, if it's passed, it should contain the previous keys and values, right? And you see that you just concatenate the keys and the key for the like pixel of interest, we can say, or item of interest in this case. And you save quite a lot of computation in this way, but we still have this like compute heavy softmax on this like quadratic matrix, which is like n by n matrix, which is produced by dot product of queries and keys, right? So even though you use this caching, it's still kind of slow. But what they do here, they avoid the computation of this quadratic matrix, so they do it in an alternative way. And yeah, in this particular value, they approximate the result of softmax on the dot product of keys and queries in some way. And there are other papers which propose, like in a recent, there is a recent paper called Attention-Free Transformer, and they do not approximate the softmax, so they do just a linear operation on queries and keys. And yeah, so there are ways to avoid computing this n by n matrix, and that this speeds up things quite a bit. So yeah, and that's yeah, that's basically it. So I did not kind of prepare anything, and also maybe I can like just from that notebook I've shared. Like let me find it. I just wanted to bring to your attention how easy it is to condition when you like with transformers. For example, you can do class condition in like super easily, but for that I need to find that that link I shared before, because I don't know where that notebook is right now. Just a second. Okay. Okay, so here, let me find it. Here you can see that I just add the like class ID at the beginning of the input, and in this way we can. So you see that here the input to the transformer is just concatenation of a tensor containing a label, like it would be from 0 to 9, right, for mnist image, and then it just regular binarized image. So and after like training it this way, you just have, you can input, then you can input like the first value to be the ID of the image class, and you can generate from it. So it's really very simple and straightforward to condition when you use transformers, because like if you put this in this way we'll learn an embedding vector for each of the classes, and this embedding vector is accessible to all the like next elements in the sequence. And yeah, so that
could you I don't know how you do it in different stage, that is not the training when you like below.
Yeah,
when
maybe I will open
when
it in Collab to like interact with the code. So okay, so yeah, what I do here, so each image, we read the image and the label of the image, right? So here I've used like the mnist data from FastAI. So we have each class in its subdirectory, and then I convert these labels into integers. So we have an integer corresponding to each class, and I just shift it up by 2 because we have 2 values for this like binary values for the image, and this class labels would be just another integer in our learned like embedding matrix. Okay, so now yeah, I binarize the image. Now here we have like a tensor of 700 84 pixels with value 0 and 1, and this tensor is prepended with a label, which is in our case from 2 to 12, right, or to 11 included. So so now each input to our model would have the first value would be its class ID, and the following values would be just the pixel values. So that's a data set. Just maybe I can run it so that okay. It's not what. Yeah, and you can see that here for me it took over like 3 minutes for generating only 4 images because I wasn't using this caching, and yeah, you can imagine that it's really slow. So so you can see here, like maybe just for. So here we have an 8, so that's actually a 6, and here you can see that we just have an array which starts with some class ID and then just values for the pixels, right? And then we feed it to the model, and I have some kind of like arbitrary transformer here. It just conditional, like autoregressive modeling, right? Okay, I've forgotten some. You can see here I use a callback to construct the target from the input, and in our case, the input would be just first values of this tensor, excluding the last one, and the target is shifted by 1. So it's all pixels like starting from the first value in the input. Okay. And then you can kind of train it and sample these images, but training would take quite some time. It took like 14 minutes per epoch for this model here. So yeah. So does it answer your questions, or do you have, if you have any, I can just try to explain.
No, I was curious about just this. You just sample, or do you give any when you're outputting?
Okay, so the generation, right? So the generation is done here by I just feed in this class. So the input to the generate would be this. You see this random integers from 0 to 10. It's our classes. And here I just set the shape. We generate 4 images, right? And I shift again it by 2 because that's how this class IDs are interpreted here. And then the generate. Yeah, let me show it maybe. So it's sampling, and we sample each pixel consecutively. So here is this code for generation, right? We just do like in a loop. We take this X, and so the input at each time step, the input to the model would be all the previous pixels, right? And then we kind of take the outputs from the model, and then you can just do argmax, or you can in this case I've used I just randomly sampled the value for each pixel, but it could be even better if you like exclude the like highly unlikely samples, and it can be done by doing it's called nucleus sampling. When we sample from like top probability, you can just filter out like all the values that do not contribute to some fraction of probability, and usually you would take like 90% or something like that, and then you sample only from the most probable pixels. But because here we have only 2 values to sample from, right? Essentially, so by setting here top k equal to 2, it would just filter out this logits corresponding to the class IDs, which are not very probable because those are never encountered inside the image, right? And then I sample just from these two most probable pixels, and then it is sampled just pixel by pixel, like autoregressively, and that's how the image is generated. And basically you can start from you can take just the upper part of the image and feed it as the prompt, and then you will generate starting from that, right? And here I explicitly set the size of the generated output. Okay, so does it explain the process?
Yep, at least I got it. Questions, somebody else?
Yeah, how do you encode the position, or is it, I didn't quite see it, but.
Okay, so the position here is just, I've used something what is set here by default, and if I remember, yeah, so absolute positional embedded, it just learned positional encodings here. So okay. that would mean we for each position we have like 784 positions, right? And for each position, we will learn a unique vector, which would be added to the content embedding. Yeah, we can. go to the model. That one would be it. Right. So here you can see that there is one embedding layer for the content. And depending on how you choose positional encodings, it can be either, so this absolute values, it would contain just another embedding layer with like the embedding size would be maximum sequence length, and yeah, the dimension of embedding would match the dimension of content embedding, right? Or you can use fixed positional embeddings, which will use just those sinusoids and cosine waves to encode the position. Or you can use, yeah, here in this library I have Excel positional encoding option. It's just another way to represent like factorized positional embeddings. Like in a sense, those are similar to absolute positional embeddings, but represented in a memory efficient way, so factorized.
So this is the Hugging Face transformer, right?
No, that's a library I used to experiment with
Okay.
transformers.
Is it you wrote the library, or?
Yeah, me and other folks, we collaborated.
Okay. Nice. Is it open source, or?
Yeah, it's.
What is it called?
Yeah, here you can see it's installed somewhere. Yeah, here's a link to.
Okay, Transformer Sandbox. Okay. Oh, okay. Yeah,
Yeah,
kindergarten.
it's kind of raw, so I'm not sure if you can use it kind of
Okay.
for your like. Yeah, you can use it if you want to learn how the things are implemented, but it's by no way kind of production ready or something. So it's just experimental stuff.
Cool, cool.
Yeah, so that's it. If there are no more questions, I'm done.
Thanks, sir. I think interest of time, I was wondering as in fact, probably the part or share really we can finish the two to show and more. Let me know when you screen.
Yep.
Yeah, we can see a screen, but kind of your sound is cutting off.
Oh, is that better?
Yeah, I think so.
Yep, it's better.
So, okay, so particular thing was the link I was with, and what there was what Moten showed. Wanted to understand how they this kind of interesting. The code is just these 4 lines, and obviously here doing what our Moten shared, right? Appending the location. It's not just fixing the things. It's hard coded for a 28. So what they do, I just want to figure this part out, fill the details, and so that I can potentially use the same going forward for any grid, but they just kind of the grid to 1, and then the grid is, I printed out things. So grid is when you do a mesh grid of 28 by 28, convert it to of 0 to 1, it you these. So the of is just all zeros. The first, remember that they've divided the to 1 between 0 and 1 to 28, and so it's those all 0.03 And the next second tuple is just 0 each of to 1. In mind that ultimate after is to generate coordinates of X and Y was showing for every dot 28 by 28, then they are eventually getting after. And so why they just this into stack, so it like 2 by 28. The first is entry in the 2, second is the second, and then they permute to get the 2 here to 2 by 28, and they add additional action, which is what the squeeze does. Obviously, this is just to make it just after the permutation, and then this X here I just again coded it to 28. And you repeat it, and these dimensions the same. Then what you is all of the Y for each pixel in by 28 array. So that's kind of what after this quick thing to hard coded look for every pixel. I just wanted to kind of explain, I mean, tremendously compared to what Morten and went through, but into the weeds, recall it going. But the more interesting also, but I just wanted to another thing, the last element, and as Arto was wondering whether it be possible if transformer, he thought this, you know, they about this fast sample, like said, showed how in transformer stuff, the for transformers paper. If you could post a link that and to be great, because that shows the caching as well as the additional of the NX calculation. The other thing that they talked about, and this was the last thing he touched on, so how you could practice the computation by kind of dividing up the image into.
So sorry to interrupt, but it's still breaking up pretty badly. I'm not sure if anybody else. I really can't understand. I get like the first half of each sentence, but that's about it.
Okay, let me, maybe it's my microphone. Can you hear me better now?
Oh, that's way better. Yes. Thank you.
Hear me better now? Or is it still bad?
That broke up a bit. That was hard to.
Okay, maybe there's some problem, in which case, okay, let's, if it's bad, no point going through it. But what I wanted to say was just try the, it'd be interesting to try the last fast sampling combining with what Arto talked about. So trying to compute in chunks with transformers. I'll see whether I can fix the microphone issues going forward. Sorry about that.
Yeah, it looked like now we are sounding okay again.
Okay, yeah. Oh, okay. Let me know if it starts breaking up. But what I wanted to say was essentially the fast sampling is, you know, an issue of dividing up the image into, in this case, they show how to do it into 4 chunks, kind of assume that each chunk is independent, and then compute for each of the 4 chunks and put that together. So that speeds up the overall computation. In this case, obviously, they don't use what Arto shared, which is the caching. So combining caching with this ought to significantly speed up the inference. So I was just wondering whether, this kind of an approach can be combined with what Arto shared, which is the caching. So it will be caching, and in addition, kind of dividing up the image into 4 pieces, calculating each of the 4 pieces. The one thing I wasn't sure about, and if you folks can go through and post the comment, was at least going through the code, it seemed to be the case that the first chunk was computed independently, or what I was wondering is whether all 4 chunks are computed independently, or once you compute the left top, then does the right top depend on the left, and the left bottom and the right bottom depend on both the left top and the right top. So, once you've computed those, whether you use that in the other pieces, but in which case you would still be dependent on the completion of the calculation of the left top for calculating the right top quarter, and then for the bottom left, you would depend on the top finishing, and then for the bottom right, you would be wait for 3 pieces finishing. But I wasn't quite sure whether that's what was going on or whether all 4 pieces are computed. I would assume that's the case if you really want to have an autoregressive model. But that's another approach to speeding up the inference, which is kind of the purpose of caching that Arto shared. And you can see the significant speed up. And here also, I thought that it would be better, I didn't get to it, but to time the inference using this approach and then using the regular approach. And in fact, he pretty much alludes to it in the fact that you can see, if we did it this way, then the calculations are dramatically reduced compared to the doing it pixel by pixel for the entire 224 by 224 MNIST images. Any comments?
I think we have 2 minutes left before we'll all be kicked out.
Yep. So I think next week we don't have the meeting. Thanks, Motin. Thanks, Arto, for taking us through the interesting parts of attention-based pixel CNNs. And week after, I believe, Jonathan, would you be taking us through the flow?
Yep, I am working on getting my flow model stuff together. So, yep. So
okay,
hopefully I'll
cool.
have something good
So
for, I guess, 2 weeks from today.
Yes, that'd be great.
Cool.
Okay, thanks a lot, everybody. See you all
Thanks.
2 weeks from now.
All right.
Thanks,
you.
Motin, for taking us through.
Yeah,
Thank
thanks,
you.
guys.
Stuff.
It was good. Thank you.